Great, thanks for the introduction. All right, yeah, as mentioned, TK and I are both talking about the same topic, which is degradation of thermochemical energy storage materials. I'll be talking about our work on standardizing characterization methods, and that'll lead into TK's talk about our work on accelerated reaction cycles of these materials. But before we get into that, I'd like to motivate why we're interested in thermal energy storage. And that's because it's been identified as one of 5 grand challenges in thermal engineering. And that's in part due to its capacity for long duration energy storage. So it's just in a sweet spot where we can target multi-day storage at a potentially low enough cost that you could fully decarbonize the electric grid. Right, so it fills the sort of void between the short-term thermal storage technologies and other long-duration storage technologies. You can also use thermal energy storage to decarbonize industrial processes. So you can take waste heat and then deliver that to a factory or other industry location and deliver heat at a range of temperatures as needed. And within thermal energy storage, we'll focus on thermochemical materials. And so we're interested in these because they have the highest energy density. They have other advantages such as minimal self-discharge during the storage process. They're also very early stage, so there's a lot of fundamental materials research going on, and there are still competing concepts for how these materials would be integrated into systems. This talk will focus on the materials research and not so much on the system concepts. The material we selected to study here is calcium carbonate. We chose it because it's an abundant, low-cost material. You're probably familiar with it. It's limestone. In the decomposed form, it's calcium oxide or quicklime. You probably know that for its use in manufacturing cement or in water treatment. We like this reaction pair because its operating temperature is suitable for things like electricity generation or industrial process heat. It's not at too high of a temperature where heat exchangers become difficult, but it is high enough where you could still generate electricity. I did mention we're not really going to talk about the system level integration in this presentation, but I did want to mention at a high level, just to introduce this because it is relevant to the form factor of our materials. So one of the prevailing ideas for how TCMs could be integrated in power generation or in other processes is using packed bed reactors, right? And so what you need to know is this is really different from a heat exchanger with other thermal storage materials like sensible heat or latent heat, because we have to transfer both heat and mass, right? So here we have a working fluid, which in this case is carbon dioxide, and so we need to exchange carbon dioxide and heat with the thermochemical material. And so you can imagine by changing the form factor, that's going to change a lot of things about the performance of the reactor, such as if we were talking about powders versus densified pellets of material, we're going to change the specific energy density. Will also affect things like the pressure drop across the reactor, will affect heat transfer rates and gas diffusion within the material. In this talk, we'll focus on the pellet form factor. We've looked at both powders and pellets so far. We'll focus on pellets here, and they're about 80% of the theoretical density of calcium carbonate. Here's what the full charge discharge cycle looks like. Right? So we start with the product, which is calcium carbonate. We introduce heat at 850 degrees. That could be from excess electricity or off-peak electricity. And that drives the calcination reaction. So this is an endothermic reaction, and it is also the charging process in our thermal battery. During the charging process, we give off carbon dioxide, and we're left with the reactant, which is calcium oxide. We can reintroduce carbon dioxide, and that drives the discharge cycle of the battery. And in this case, we're interested in discharging heat at 650 degrees. And that can be used for things like generating electricity or industrial process heat. But it's important to note that this reaction cycle isn't specific to calcium carbonate. We could describe any gas solid charge discharge cycle like this. And so we don't have to operate at temperatures of 850 degrees for our charging inlet. We could use other sources of energy like industrial waste heat. Okay, so the main challenge with calcium carbonate, and the reason we're interested in improving it, is that it has a fairly severe degradation in the storage capacity with cycling. And within about 15 cycles, the storage capacity degrades to about 20% of the original value. So our goal is to try to mitigate the degradation in storage capacity. And to do so, we need to characterize the materials and generate plots like this, where we quantify the conversion ratio, which is sort of a dimensionless number from 0 to 1 that describes the storage capacity of the material. And we want to define that as a function of the cycle count, which sounds like it would be pretty straightforward, but there are some challenges with the characterization. So you might think we could use DSC to measure the heat flow going in and out of the sample during the charge-discharge cycle. And so the challenge here, if we look at this plot on the right, I show the DSC heat flow for a full charge-discharge cycle of calcium carbonate. And so here you can see we have a temperature ramp up to 850 degrees, that's our calcination reaction. We go down to 650 and we have our discharge reaction. We're really interested in integrating this peak right here. That would describe the basically the reaction enthalpy that remains within the material after cycling. Integrating this is really hard because there's an initial kinetic-driven reaction that's very fast. So we get this really steep peak for a very short duration of time. And integrating that is not very accurate. There's also a challenge that after the kinetic-driven reaction, we have a diffusion-limited reaction. So that DSC signal doesn't go to 0. It's just a very small value. And integrating that over a long duration introduces a lot of inaccuracy. So it gets very hand-wavy if you try to integrate this curve. So instead, we use what we call the molar conversion ratio. So this is based on a simultaneous TGA measurement alongside the DSC. And basically what we're measuring here is the uptake in mass of carbon dioxide from the reactant calcium oxide. So at the bottom, we would start from a sample of pure calcium oxide. And when we introduce CO2, the mass rises quite rapidly, and then we have a turnover where we have a slower reaction after that. And we define the conversion ratio as just the ratio in that mass from the carbonated state relative to the calcium oxide state times some ratio of molar masses. And by making it a molar conversion ratio on a molar basis, then we can say that this is the energy storage capacity, because we can just multiply that by the reaction enthalpy, which is 179 kilojoules per mole. So now we can turn this mass measurement into a direct measure of energy storage capacity. There's another challenge though, and that's that the conversion ratio is dependent on time, so how long we carry out the carbonation reaction. And the rate of the reaction can vary on a lot of things, such as the reaction conditions or the form factor of the sample. And so to describe it in more detail what that looks like, we'll zoom in on one reaction cycle. So the important thing to know here is that the carbonation reaction is the rate limiting reaction. So during calcination, we always fully return to calcium oxide. That's not an issue. When we introduce carbon dioxide and try to go back to calcium carbonate, we never fully get back to the fully charged state. Discharged state. And the reaction can be described by two different reaction regimes. We have this kinetic-driven reaction, which in this case, we have all this surface area of calcium oxide that is exposed to the gas. So the CO2 can just react freely with all the unreacted surface area. At some point, you build up a product layer of calcium carbonate on those calcium oxide particles, and then CO2 has to go through a very slow ionic diffusion process through that product layer to get to the reactant. So that's when we get this inflection point, we have the slow reaction. And the point where this inflection point happens depends on things like reaction temperature and form factor, gas pressure, all sorts of things. So if you were choosing a constant reaction time for your experiment, say it could be A, B, or C, you can use the conversion ratio as a comparative metric only if you have constant reaction conditions in form factor, but you can't compare across those, right? So our argument is that we need to find a way to come up with a standard definition of where this inflection point occurs so that we can compare cycles sampled through various different conditions at a standard cutoff point. And we're going to call this the kinetic conversion ratio. So this is where the kinetic-driven portion of the reaction ends and the diffusion-limited region begins. So we're not the first ones to come up with this idea. Other people have tried this. But as of now, there's currently no definition for the kinetic conversion ratio that's based on physical parameters within the material or this reaction, right? And so we've developed a universal characterization method to define where this point occurs that we demonstrate with calcium carbonate, but it could be extended to other gas-solid reactions in general. We do this using an already established rate model for gas-solid reactions developed by Zhenshen Li. He applied it to calcium carbonate in carbon capture experiments, but it can be extended to gas-solid reactions in general. There are really two key equations that you need to understand. So the first is this dx dt, that's the reaction rate, the change in conversion ratio with respect to time. And the second function is d delta dt, and that's the rate of change in the reactant surface area. And these two equations are solved simultaneously, and they can be empirically fitted to any transient conversion ratio data. There are a lot of different inputs that go into these functions, and without getting into too much detail on those, I'll just say they can be broken down into three categories. We have some geometric functions that basically just say we're dealing with spherical grains in the material. We have some physical properties such as the gas pressure, the surface area porosity of the material. And we have three fitting parameters. Those are the reaction rate constant, a gas diffusion constant, and an ionic diffusion constant. There's one other parameter here that I didn't label. It's this capital Ks. That's essentially analogous to the Kohler number. It's the ratio of this reaction rate constant to the gas diffusion constant. In Lee's model, this ratio doesn't work out to be dimensionless. There's an extra factor of molar mass, but it's essentially analogous to the Kohler number. And he used these equations to apply them to empirical data found in literature for calcium carbonate. So this came from another work where they looked at the reaction, the carbonation reaction at different carbonation temperatures. And it fits really well. And we decided we could take this model and just go one more step with it in order to identify where this inflection point occurs. And I'll show you how we do that by fitting this model to our own empirical data. So here's what that looks like. So as I mentioned, these two equations are solved simultaneously. And on the right, I show the plots that represent that. So here we have the conversion ratio with respect to time, and the gray shaded area is our measured data, and the black solid line is the fit from the model. Simultaneously, we have this function d delta dt. And if you look at the form of that, if we integrate that, it's just going to be a first order exponential function. It's just an exponential decay. And that's exactly what we see. We can fit this as a first order exponential. That means it has a time constant. So we can say the time constant is about 1 minute. That means that this delta surface area function achieves about 5% of its steady state value after 3 tau, which is about 3 minutes. If we go back and look at our formula for dx dt, we see that there are two terms here. One is proportional to delta, and one's proportional to 1 minus delta. These essentially describe the driving force for the kinetic-driven reaction and then the diffusion-limited reaction, right? So we argue that after this 3 tau period of 3 minutes, that's what we can call the kinetic completion time, right? And that's where we just separate the kinetic conversion ratio from what you might call the total conversion ratio at the end of the carbonation period. All right, so now we're going to use this kinetic conversion ratio to study degradation in these materials. So these are the results of but cycling calcium carbonate through this reaction cycle for very long. We chose very long calcination and carbonation conditions just as a baseline sort of experiment. And then we said, okay, let's take the same data and say what was the conversion ratio at that kinetic completion time, right? So this was the conversion after 75 minutes, and this is the conversion after just 3 minutes. What we see is that that kinetic contribution to the overall conversion makes up the vast majority, even with a very long cycling duration. And we also notice that it does decrease with cycling, right? And that's kind of expected. It's a result of the decrease in the reactant surface area with cycling. So that will affect the Dom-Kohler number, which goes on to affect the kinetic term in dx/dt. So the main takeaway here is that the difference between the total conversion and the kinetic conversion is not just a proportional change, but there is actually a different rate of decay. So we think that's an argument for why you really need to look at the kinetic contribution to conversion if you're going to compare materials under different cycling conditions. So now with that established, we look at experiments where we actually start varying the duration of the reaction. So in this case, we continue to use the 16 cycles of long cycles as our baseline experiment. So that's the 30-minute calcination, 75-minute carbonation. And we tried 2 other cases. So we did a short carbonation case where we reduced the carbonation to just 3 minutes, which is equal to the kinetic period. We did another experiment where we also decreased the duration of the calcination reaction from 30 minutes to 10 minutes. All right, so what we observed is we noticed 2 really interesting things. So by decreasing the duration of the carbonation reaction, there was no effect on the conversion ratio relative to the baseline case. So what that means is we could generate the same degradation data in 35% of the experimental time. So this really sets up TK's talk, which is right after mine. This will enable his accelerated reaction cycling study. The other thing we noticed is that, we do have a over 10% increase in the conversion ratio when we decrease the duration of calcination. So we know from literature that nascent sintering is one of the dominant degradation mechanisms in these materials. And now we can say that the sintering process is dominant just during the calcination reaction. We can assume that it's not really occurring during the carbonation reaction. So this gives us insight into exactly when sintering is happening during this reaction cycling process. It's really just in the calcination reaction, even though we observe the effect of it during the carbonation reaction. I will say that we don't really expect this to be a mitigation strategy for degradation, because given enough cycling, you would expect the conversion ratio to converge back to the baseline just due to the accumulation of time at high temperature. You can see at 16 cycles, it's already starting to turn over. Instead, what we're really interested in is looking at thermal pretreatment strategies. So now here we're varying the cycle duration, but sequentially. So we have a baseline case where we do just the long cycles, and that follows the sort of sintering-dominated degradation that we come to expect. But we notice something interesting, and that's if we do sequences of short cycles followed by long cycles, we get a lasting permanent increase in the conversion ratio of the material, right? And it's especially clear in the case where we did 16 short cycles followed by 16 long cycles. And again, these are all kinetic conversion ratios. It's all the conversion ratio taken at that 3-minute mark. So they're all directly comparable. So we're measuring the real change in the material, and this isn't just an artifact due to a change in the duration of the measurement. And I'm running a little short on time, but TK is going to talk more about this in his talk, so I'll let him go into it in more detail. I will just note that we also took SEM images in the the calcium oxide in the pristine state, and in the two cases, the 16 short and 16 long cycles, and the 32 long cycles. We see that in the pristine state, we have all this reactant surface area available for the carbonation reaction, right? And that's why we have such a high conversion ratio and fast reaction rate on the initial cycles. But after cycling, we see just more densified regions in general in both of the cycled samples. But there is a difference between the sample that went through the sequential cycling duration experiments and the one that just went through the 32 long experiments. And we attribute the difference in the kinetic conversion ratio to pore plugging. So we know that repeated formation and decomposition of the product layer of these pores causes agglomeration of the calcium oxide, and that restricts access for gas diffusion into these nanopores. So in summary, we define a universal conversion ratio to characterize gas-solid TCM reactions based on an established rate model that was demonstrated for calcium carbonate, but it could be extended to other gas-solid materials. We confirm that ascent sintering of calcium oxide is one of the dominant degradation mechanisms in this material, and primarily occurs during the calcination reaction. But there are opportunities to mitigate degradation by looking at how we age the material in those initial cycles, in the initial break-in period. And so I think that's where a lot of our future efforts will focus, and that's where TK's talk is going to pick up with the accelerated reaction cycling, because to do those studies, we're just going to need a lot more samples, and we need to get to much higher cycle counts, which we just can't really do with the experimental bottleneck of TGA-DSC. Right. I'd like to acknowledge our group, the Water Energy Research Lab, our collaborators at NREL, and our funding from the Degrees Energy Earthshot Research Center. With that, I'd be happy to take any questions or defer them to TK.